Pluto, a distant and secretive planet, was once considered part of our local planetary system. However, recent surprising statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into the spotlight. They proposed that this icy world might be on a potential collision course with Neptune. How could this be possible, and what consequences would such a catastrophic event have? Could this be a fascinating cosmic anomaly, or is there something more to this looming disaster? Join us as we delve into the potential outcomes of a Pluto-Neptune collision. Once categorized as a planet and later reclassified as a dwarf planet, Pluto remains a subject of intrigue in the vast cosmos. This is evident from the recent speculations by renowned experts. Pluto's orbit closely intersects with Neptune's, which has raised concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a potential disastrous impact between the two with significant repercussions for Earth. But how could such an event happen? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not even finished a full revolution. Yet the fascination doesn't end there. Pluto's orbit is exceptionally elliptical, diverging greatly from the nearly circular orbits of the major planets. A more intriguing feature is its tilt, 17 degrees to the ecliptic plane, making its path noticeably tilted compared to the other planets. This inclination and eccentricity introduce additional layers of complexity to its orbit. One of the most remarkable aspects of Pluto's orbit is how it intersects with Neptune's. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, defying what one might expect based on their positions in the planetary system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The study of Pluto's orbit began immediately after its discovery as astronomers sought to understand its unique path. Unlike most planets whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentric shape. The mystery deepened as scientists realized that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, demonstrates the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects in space, like Pluto, Neptune, and the Sun, interact with each other gravitationally. This is similar to predicting where objects will move based on their starting positions and mutual gravitational effects. In Pluto's case, the problem shows how its orbit, Neptune's, and the Sun's gravity all interact in a complex manner. Astrophysicists highlight terms like asynchronous libration, orbital precession, and the VSK oscillation to explain this phenomenon. Asynchronous libration refers to how, whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is key to preventing a collision. Orbital precession refers to the slight upward movement of an orbiting body. For Pluto, this means that when it nears Neptune or another large planet, it is positioned above their orbital plane, providing an added protective measure. Another important factor is the VSK oscillation, which describes how Pluto, Neptune, and the Sun's gravitational forces influence each other. This oscillation helps to maintain Pluto's orbit, preventing any erratic movements that could lead to a collision. Despite Pluto's seemingly erratic path, this oscillation stabilizes its movement over long stretches of time, revealing that even chaotic-seeming systems follow hidden patterns and rules. These factors help to keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or drift too far off its course. The three-body problem is crucial for understanding the changes in these orbits and the interactions between celestial objects. Studying this helps scientists learn more about Pluto, our solar system, and even distant stars and planets. Mathematical simulations in the 1980s revealed that despite these stabilizing effects, Pluto's orbit is unpredictable. Even small variations in its initial conditions could lead to significant changes over millennia. Nevertheless, Pluto's orbit has been found to maintain stability over extremely long timescales. Further investigations have helped us understand how Neptune, Jupiter, and Saturn affect Pluto's orbit. There is a unique relationship between Neptune and Pluto, For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's orbit, preventing it from veering too far into Neptune's territory. Saturn's gravitational pull adds another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune are working in tandem to ensure Pluto's safe passage through space without encountering any significant problems. Without these gravitational interactions, the solar system could be a much more chaotic place, where objects like Pluto could crash into other planets or be ejected from their orbits, triggering a cascade of events. For Pluto, understanding its orbit is essential, particularly with discussions about the possibility of it colliding with Neptune in the future. This also gives us a clearer understanding of the dynamic nature of the nearby planetary system. The case of Pluto highlights how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and research to better comprehend our place in the universe. The study of celestial bodies often leads us to confront their strange behaviors, and Pluto's orbit is a prime example of this unusual nature. The concept of orbital chaos, which refers to the sensitivity of a celestial body's orbit to its initial conditions, is clearly demonstrated by Pluto's path. Even slight changes in its position or speed can lead to dramatic shifts in its long-term orbit. Automated simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations employ sophisticated mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking small details in the simulations, scientists can observe how even tiny changes can significantly alter Pluto's trajectory. In the late 1980s, these simulations uncovered fascinating insights about Pluto's orbit. While stabilizing factors like asynchronous libration and orbital precession help maintain stability, Pluto's orbit can still be erratic if its initial conditions vary even slightly. However, despite the apparent chaos, Pluto's orbit remains stable over extensive timescales, such as billions of years. This implies that despite the seeming unpredictability of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, especially those with irregular orbits like Pluto, is an enormous challenge. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While mathematical models are invaluable in understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models depend heavily on the accuracy of the initial conditions, and even the smallest error can lead to vastly different outcomes. The chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the ever-changing dynamic nature of the universe. While we have made incredible progress in understanding space, Pluto's case demonstrates how much there is still to discover. The gravitational effects of the giant planets on Pluto's orbit provide valuable insights into the broader workings of the solar system. They reveal how the positioning of each planet can have profound effects on the stability and trajectory of other bodies within the system. So why have prominent astrophysicists recently raised concerns about a potential collision between Pluto and Neptune? Despite all these forces working to keep the 2 planets from colliding, Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly Pluto. Tyson, who played a role in Pluto's reclassification as a dwarf planet, offers valuable insights into the evolving understanding of celestial mechanics and the public's renewed interest in overlooked aspects of space. Tyson views the renaming of Pluto as not a demotion, but an essential adjustment in response to the expanding knowledge of the diverse objects orbiting the Sun. He believes that the complexities of orbits like Pluto's reflect how much is still left to explore in space. The ongoing fascination with these questions fuels the excitement of space exploration. Despite Tyson's optimism, his concerns about Pluto's potential crash with Neptune suggest that there are still many unknowns regarding Pluto's orbit. Will Pluto collide with Neptune? Or is this just another instance of confusion in the ever-changing cosmos? Only time and further investigation will provide an answer. For now, we are left with an increased curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the aim of uncovering the secrets that lie beyond. The possibility of a Pluto-Neptune impact raises further questions about the mysterious and fascinating universe in which we live. The prospect of an impact between Pluto and Neptune challenges our conventional understanding of planetary stability, especially considering the current relative strength of their orbits. Given Pluto's location on the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a powerful gravitational field, the implications of such an impact would be significant for our understanding of gravitational interactions and the solar system's evolution. To comprehend the dynamics of a potential collision, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances that are believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is made primarily of hydrogen, helium, and other lighter elements, with a dense, deep atmosphere. A collision between these vastly different bodies would alter their structure and behavior significantly, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly intriguing is the influence of other bodies in the solar system. While Neptune's gravity plays a key role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and powerful gravitational pull, also has a stabilizing effect on Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a straightforward collision course. The gravitational resonance between Pluto and Neptune, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a cosmic lock that keeps them from directly colliding. This resonance is a critical factor in ensuring that Pluto and Neptune's orbits, while they intersect in the vastness of space, have never resulted in a direct collision, despite the apparent stability in the orbits of Pluto and Neptune. The dynamics of their relationship continue to be a topic of significant scientific investigation. The gravitational resonance between the 2 celestial bodies is a key factor in their orbital stability. This resonance is a result of the fact that Pluto and Neptune are in a locked configuration, meaning that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This precise, coordinated movement ensures that their orbits do not intersect in a way that would lead to a collision, despite the apparent overlap in their paths. This phenomenon is similar to other gravitational resonances observed throughout the solar system. For example, the moons of Jupiter and Saturn often exhibit similar resonances, which help maintain the stability of their orbits. In Pluto and Neptune's case, the resonance acts as a cosmic safeguard, preventing their orbits from overlapping in a way that would result in a catastrophic impact. As a result, even though Pluto's orbit is highly eccentric and tilted compared to the orbits of other planets, it remains in a relatively stable path, safeguarded by the gravitational interactions between Pluto, Neptune, and the Sun. Further complicating the potential for a collision is the influence of other massive planets in the solar system, particularly Jupiter. Jupiter, being the largest planet in the solar system, exerts a significant gravitational force that can influence the orbits of smaller bodies like Pluto. The massive planet acts as a sort of shield, preventing objects like Pluto from veering too far into Neptune's orbit. The interaction between Jupiter's gravity and Pluto's orbit helps ensure that Pluto remains on its current trajectory, even as it moves through its highly elliptical and tilted orbit. Another factor that contributes to the unlikely nature of a collision between Pluto and Neptune is the nature of their compositions. Pluto, being a dwarf planet located on the outskirts of the solar system, is composed primarily of rock and ice. Its surface is covered in frozen nitrogen, methane, and carbon monoxide, giving it an icy appearance. Neptune, on the other hand, is a gas giant with a thick atmosphere composed primarily of hydrogen and helium, along with trace amounts of other gases. The differences in their compositions suggest that if a collision were to occur, the result would likely be a violent and dramatic event, altering the structures of both bodies. The current scientific consensus suggests that while a direct collision between Pluto and Neptune is extremely unlikely, the interactions between these bodies are still of great interest to scientists studying the evolution of the solar system. These interactions offer valuable insights into the complex gravitational dynamics that govern the movements of celestial bodies. By continuing to study the orbits of planets, dwarf planets, and other objects in the solar system, scientists hope to uncover new information about the forces that shape the universe. In addition to the gravitational forces between Pluto and Neptune, the overall dynamics of the outer solar system play a crucial role in maintaining the stability of these orbits. The influence of Saturn, for instance, helps prevent Pluto from drifting too far into Neptune's territory. This gravitational tug-of-war between the various planets in the outer solar system ensures that the orbits of bodies like Pluto remain relatively stable over long periods of time. The collective influence of these planets creates a delicate balance that helps maintain the integrity of Pluto's orbit and prevents it from deviating in ways that might lead to a collision.